A new paper says that plant behavior can be so sophisticated it should be considered to be intelligent. That may be so, but the paper also reveals a fatal problem with evolution and how evolutionists cover it up. Here is the press release. Even without a central nervous system, some life on Earth can behave in intelligent ways. When beetle larvae begin to munch on the leaves of goldenrod plants, the plants emit volatile organic compounds, which signals to the insects that the plant is damaged and they should move on. At the same time, the attacked plants also alter the reflection of the red light from their leaves, which is detectable at a distance by other plants. In response, these neighboring goldenrods shore up their fortifications against predators, growing faster and producing defensive compounds. Goldenrods are not only integrating information from the environment, say the authors, they are anticipating and preparing for future conditions based on their current environment. That's the sign of intelligence they're talking about. The response of the plants to VOCs is more than just a reflex or fixed action pattern. It is a considered behavioral change based on the costs of herbivory and peer competition. When no other flowers are around, goldenrods under attack don't emit the same light from their leaves. Depending on the information it receives from the environment, the plant changes its standard behavior. There is a lot going on there, and I'll simplify it in a minute. Here is the journal paper, and this diagram illustrates how plants use both long-term and short-term memory in their decision-making. This passage talks about a number of fascinating capabilities of the plants, such as learning and memory. And also, when they're attacked by the herbivores, they may produce compounds to resist the herbivores, such as toxic compounds that will deter the herbivores, or volatile organic compounds which may confuse the herbivores or attract herbivore predators to reduce the attacks. So a lot of things going on here, and I'm going to summarize this in this diagram that I created. Very simple, much simpler than the paper, just to show at a high level some of the things that are going on. So there in the figure there, you have a plant with some herbivores attacking it. The plant detects the attack. Now that may seem obvious, but it isn't. You know, if we get a mosquito bite or something, we immediately detect it. We take that for granted. A plant doesn't have, for example, the central nervous system that we have. It isn't necessarily going to know it's being attacked. So there has to be the mechanism, the sensors in place to detect the attack. Then internally, it sends internal messages to produce these toxic compounds and so forth. So that's what that circle is indicating. It may also alter the radiation given off by its leaves to be detected by nearby neighboring plants as kind of a warning so they can take action. So that's step number one there, or step number two. Thirdly, the plant may release these volatile organic compounds, which may have a couple of purposes: confusing the herbivores or attracting the predators. So a lot of things going on. Things that have to happen are detection. It has to be able to detect the herbivore attack and then transmit these signals, both internally, that signal we talked about, and then the radiation signal, and then the VOC, volatile organic compounds. Those different mechanisms have to be activated. Now, on the reception side, those signals are received, and then there is some action. So the plant receives its own internal signals and then generates the toxic compounds and so forth. Or a neighboring plant may detect that radiation and then act on it. Or the predator will detect those VOCs and act on it. All of these things have to be in place. Now, how is evolution going to do that? Could this system evolve? So just for an example, look at the red text here. You have the plant alters the radiation signal, the radiation coming off of the leaves, to enhance the defenses in the neighboring plants. The neighboring plants have to detect that and act on it. So there's the detection of the attack, the initiation of the communication of the signal to initiate that radiation change, and enacting that, and then the reception of that, and then doing something about it. Now, that's a large number of mutations that would have to take place to put all those pieces into place. They all have to be in place. If you have the detection but not the radiation change, if you have all the parts but one, it's not going to work. All of these different pieces of the puzzle have to be in place for it to work. And this goes for the other items as well. So there is a large number of mutations that have to happen before you get anything to work. It isn't going to work under evolution. Evolutionary theory, random mutations can't do that. This is outside of the capture of evolution. It's not feasible under evolution. Under evolution, mutations must be blind. They cannot know what is needed. They're just randomly happening. So these are random mutations. A single mutation is not going to help, as I mentioned a minute ago. A large number of mutations are required to realize the benefit. This is why it's a problem. So consider this big, astronomically large blue box. That's the set of all possible designs. So evolution must search through an astronomically large design space. And there, that little white dot represents something close to this system that we're talking about. Evolution must find a tiny location in an astronomically large design space. Most evolutionists are ignorant of this problem. You just don't see this addressed. Typically, most evolutionists don't talk about this. They don't write about it. They don't analyze this sort of a problem. What mutations would be required for this system to evolve? In what sequence? How many mutations are required in total? What are the probabilities? These sorts of questions are not asked. They're certainly not answered. So the paper simply ignores this problem. You can go look at the paper. You're not going to find it in the paper. It ignores this problem. Instead, the paper appeals to fitness. And let me read from this passage here. A particular plant behavior has to be evaluated for its eventual contribution to maximize the fitness outcome. It's all about fitness. The problem is masked by an appeal to fitness. Let's look at this again. This is very important here. A particular plant behavior has to be evaluated for its eventual contribution to fitness. That's the key. And this is not just this paper. This is a very common approach to these problems, a very common strategy. This is a common strategy. The system has positive fitness, it is argued. Therefore, it could have evolved. The question of whether a system can evolve is centered on its fitness. If it improves fitness, then it can evolve. This masks the problem that the system could not have evolved in the first place. It's outside of the reach of evolution. The evolution of this system is not feasible. Religion drives science, and it matters.